16.2. Now, can I get you to take out your notes for 16.2? Please recall, please try to remember that acids, when you look at a chemical reaction, an acid in a chemical reaction, according to Bronsted-Lowry, an acid donates a proton, right? So you have a proton leaving something, that's from the acid, and then the base is accepting the proton, okay? Because these are reversible reactions, you actually have two acids, right? You have an acid acting in the forwards direction and an acid acting in the reverse direction. So we talked about that. We also talked about amphiprotic substances, right? Amphi means can go both ways, kind of. So you can either accept or donate, depending on the conditions, right? A frog can live in water or out of water, depending on the conditions. And then we went through some practice. Then we did conjugate acid bases, right? Conjugate just means partner. So what does acetic acid turn into? Acetate, that's all, right? They're conjugated with each other. And then we did something incredibly important called predicting acid-base reactions. This is what our focus is on for today. Now we're going to spend the next kind of 25 minutes talking about this, giving you a little bit of time to do some reaction predictions, and then we're going to mosey into the lab at about 11:30. We're going to get 10 or 20 minutes in the lab to do a couple reactions. In order to predict the outcome of an acid-base reaction, let's say I had, I don't know, whatever. I'm just going to make something up. Let's say I had all of these things in a solution. And water, whatever. That's complicated enough. Okay. So let's say I had all of these things mixed together in a solution. Now, what I want to ask you is, I want to ask you to predict the predominant or the first acid-base reaction that will mostly happen. Okay. That's what I want to know. What's the one reaction in here that will happen kind of first more than anything else? What's the predominant acid-base reaction? So we have to predict it, okay? Now the way we predict it is by identifying the strongest acid and then identify the strongest base and react them together. That's the whole point of this. So if we looked at this, you should be able to find a little bit of room somewhere to do this, okay? Somewhere, whatever, doesn't matter. Our 5-step method, first step, list the major entities. I've already done that. I've listed the major entities for you, okay? Just find anywhere, find room anywhere to do this. Step number 1 says list all the major entities. Step number 2, do you remember what step number 2 says for predicting acid-base reactions?
Label was strong acid and strong.
Not yet. You could jump into labeling strongest acid and strongest base. But let's just label any acids, any potential acids, and any potential bases on you. So what we will do is we'll look at our periodic table, but our table of acids and bases. We'll look at our table of acids and bases, and we'll try and figure out, okay, is this an acid? Could it be an acid? Could it be a base? Water. Can this thing act like an acid?
Yes.
Yes, it can. You see it in the acid, in between the shaded lines, right? Perfect. Acid. Can it act like a base? Yes, it can. Okay, base as well. H2SO3. H2SO3, can it act as an acid?
Yes.
Yes. Can it act as a base? No. When I look H2SO3, I find it in the acid column, but I do not find it anywhere in the base column, right? So I'm labeling it as an acid, but not as a base. Perfect, no problem. Cl minus, can it act as an acid?
No.
No. Can it act as a base?
No.
Are two different answers.
Yes.
Yeah?
Yep.
Yeah?
Yes.
Okay, let's put it. Sodium, can it act like an acid? No, I don't see it anywhere on the acid list. Sodium, can it act like a base? No, I don't see it anywhere in the base list, right? I don't see this anywhere on the list. All by itself, truly all by itself, I don't see it anywhere. Okay, so that's fine. We'll ignore it. OCl minus, can it act like an acid or a base? A base. And then HF, can it act like an acid or a base? An acid. Okay, so we've got 3 potential acids and 3 potential bases on here. What is the strongest acid in this list? H2SO3. And what is the strongest? Any questions so far? So far, does anybody have any questions? No. Okay. All you have to do, take your strongest acid, react it with your strongest base. That's all you have to do. H2SO3. Oh man, that's terrible. Is going to react with OCl minus. The acid transfers how many protons? How many protons is this thing going to give up? Uno. It's going to give up 1 to OCl. So we're going to get HSO3 aqueous plus HOCl aqueous. Right? 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 Isabel. I done goofed. Messed up. Wrong. 0. No marks. That's a pity. That's a darn shame. It sure as hell is, right? Absolutely. Yeah. So Isabel is totally right. Jaden's totally right. Matthew's totally right. Everybody other than me is totally right. Okay? Is that if what's the total charge on the left-hand side? 0 plus -1 is -1. This doesn't add up to be -1. That's a problem. Immediately you need to notice that that's a problem. Immediately. That's got to be a backup for you. Okay? OCl minus, we know that OCl minus is negative because it's negative. It literally says that it's negative. Okay? But when I look at H2SO3, H2SO3 turns into HSO3 minus, right? So this has to have a negative charge. Okay. Perfect. Now, one last thing to do. What do I have to do?
It's products favored.
Is it products favored or is it reactants favored? Look at your list. Is this reaction uphill, right, from left to right? Or is it downhill from left to right? Well, this is one of the strongest weak acids we can get, right? H2SO3 is way up here, and OCl minus is way down here. So this is for sure downhill. So what does that mean, a downhill reaction? Products favored. So this thing is going to be greater than 50%. Or you can say just say products favored, right? Whatever. That's totally fine. Are we okay with that? That's all we have to do. How complicated is that? A little bit. You had to search for the strongest acid and strongest base, react them together, right? Have a proton transfer from the acid to the base, and then you have to figure out if it was products favored or reactants favored. Now, I skipped over the hardest part. What's the hardest part in here? Getting your major entities is the hardest part. And I don't know if you had a Chem 20 teacher last semester or last year stress to you, oh my God, major entities is so important. Not for Chem 20, but for Chem 30. It's incredibly important, okay? So let's take out your lab, and I want to give you a little bit of time to practice on your lab or whatever, it doesn't matter. If you weren't here on Thursday, then you wouldn't have got this sheet, but it's in the bin. You can always go get it if you want. When I look at this, when I look at this, there we go. Let's read the instructions together as a group, please. Instructions. Use the 5-step method to predict the acid-base reaction. I want to be very clear. The reaction is the only thing I'm marking here. That's the only thing I'm marking. Okay? I want you, in the lab in 15 minutes, I want you to do this reaction. So what are you going to add together? For reaction station number 1, what are you going to add together? Sodium acetate and hydrochloric acid. And you're going to smell it, okay? Now you're not going to smell it like, you're going to be doing this in a little dropper plate because there's no reason for us to use like a huge quantity of materials, okay? You're going to do this in a dropper plate. So you're going to add sodium acetate and you're going to add hydrochloric acid, and then you're going to smell it. But how are you going to smell it? Right? You're going to start with a little distance away, and then you're going to slowly get closer and closer until you can smell it, right? The last thing you're going to do is you're going to say, oh, Walter told me to smell it. Because what's going to happen is, I've seen it before, is people will start to cry, and you've literally burnt the chemical receptors inside your nose. You've overpowered them, and then that stimulus will get shut down for a good portion of the day. You'll not be able to smell for like a good portion of the day, and then maybe it'll come back. Okay, so don't do that. This is waft, man. Just waft. It's all good. So you're gonna do that reaction, and I'm marking you on your prediction. Can you predict this reaction? Okay. You should see one of your products. You should maybe notice, oh, that's got a unique smell to it. Interesting. Yeah.
So we're not going to finish all the reactions today, so we can like, we're not handing this in today, right?
No, you're going to hand this in tomorrow.
Tomorrow.
Yeah. Okay. Okay, sodium benzoate reaction is mixed with sodium hydrogen sulfate solution. Okay. You should see something that's insoluble. You should see a precipitate forming. That's hopefully the idea behind it. Okay. So sodium benzoate. Is this an ionic compound?
Yes.
What is an ionic compound?
Metal.
A metal and something else, right? Or ammonium and something else, right? Positive ion, negative ion. Positive ion, negative ion. That's all an ionic compound is. Positive ion, negative ion, right? So this, remember, ionic compounds typically split up, so split them up. Sodium chloride is mixed with water, so test the pH. What that means is use pH strips and test it, okay? Solid aluminum sulfate is mixed with water. I want to be very clear. Aluminum sulfate is actually incredibly dangerous for you to interact with, okay? So just, you are going to be using an apron and you are going to be wearing glasses. There's no need to wear gloves because if you get anything on your hands, you just go wash them off. That's not that big of a deal. Iron 3 sulfate, same thing. Iron 3 sulfate is dangerous. So solid sodium hydrogen carbonate is added to solid or sodium hydroxide solution. Okay, do that. Test the pH, right? This last one, do it. Try it out. Do it. But we're going to talk about these together either at the end of class or at tomorrow at the beginning of class. Is that okay? You've got 10 minutes-ish to practice. Practice these. Try to predict these reactions, okay? Let me know if you have any questions. We're going to start the lab in 10 minutes. You're using the 5-step method to predict the reactions. That's all you're doing. You're just predicting reactions here. Yeah. We're the blue bin, right? Yep. And oh no, we're the green bin. People took them all already. Are you looking for the sheets? Yes. Okay. Well, I gotta go print them off. Sorry, Chelsea, I am busy. Yes. Yeah. Sorry, Toka. I have print off extras apparently. 10. I wonder if that'll be those. This as a whole, when you put a positive and negative together, there's no positive and negatives against each other. What I'm hinting at, saying, is that this thing is now, the major entity is sodium positive, benzoate negative, that's good. Sodium, hydrogen, sulfate, good, and water. So that's your strongest base, that's your strongest acid. Yeah, your strongest base. Acid, the acid around proton, that thing.
Oh, because that was like.
No. And this thing is insoluble. So you should see it precipitate.
Oh, okay. Should we always check if it or
No, because you can't check solubility for that thing because it's an acid. And we kind of assume that all acids are soluble, even though they're not. So that I'm just telling you that you should see that. What do you mean? What would cancel out? Yeah. Yeah. Close. Close. Yes. So sodium split up into sodium ions. So the acetate ion is so hot. Oh, okay. Negative there? Okay. Yeah. Perfect. Yeah. But hydrochloric acid.
No, that's only for
And none of these don't exist. You can't react because it doesn't exist. No, what is hydrochloric acid? Instead of a bottle of hydrochloric acid, you have a bottle of hydronium chloride. Does that make sense? Yeah. Do you understand now why I say that?
Yeah.
Hydrochloric acid doesn't exist anymore.
So you just use the.
Giabui is what I'm talking about. Yeah. Sodium acetate and is that in first one as well? Yes. So instead of sodium, what do you have? Because if you're going downhill, it's easier to crash and die on So what is a sodium ion? What is an acetate? Okay, keep in mind that everything, when you do matrix, everything is basically either here, it's an ionic complex. And acetate
so benzoate
it's not that they don't have it. It's that, what are you right now? No, it's not that they don't react. Yeah, these things are too. What is this? All of these things, what do they have in the It's already. When I buy yeah, kind of. I don't know, split up doesn't mean anything. Like, so when I buy a bottle of hydrochloric acid, this is the most concentrated hydrochloric acid you can buy, like commercially, without a license or anything like that. So here's a bottle of hydrochloric acid. Now it's called muriatic acid, and it's extremely corrosive. I want to be very clear. There is no hydrochloric acid. This is just a bottle of hydrochloric acid. Why? How do you know that there's no hydrochloric acid? What are those top 6 things called? So they immediately every time it's strong acid, all 6 of those strong acids are actually hydrogen in water. And then chloride, right? Okay? I'm getting the same questions over and over and over again, and that means that we're not ready. Now I'm not blaming you, okay? You're not to blame for this. I'm to blame for this, okay? I'm trying to go too fast. In our major entities, there's like 4 or 5 categories of compounds that can exist, right? You've got ionic compounds, you've got acids, you've got bases, and then you've got like neutral molecular compounds. For the purposes of predicting an acid-base reaction, ionic compounds always split up a little bit, but sometimes they're like soluble and sometimes they're insoluble. Do you have a table that will predict whether or not something is soluble? Yeah, you do. You have a table that will predict whether or not. Now, the problem is, a lot of you don't know what an ionic compound is. So you can't use the table unless you know what an ionic compound is. Ionic compounds always begin with what? A metal or ammonium. A metal or ammonium. So they begin with a metal or ammonium, NH4+. So we can use our table in here to predict it. Now that's not your fault. We're probably just going to do this lab tomorrow or something. Okay? Just don't pressure yourself right now, because whatever, it's all good. Now you can look in your table, but if you don't see if something's ionic and you don't see it in here, I mean, odds are you're using a group 1 ion. Sodium, for example, is a group 1 ion, right? So sodium anything will be soluble. Sodium anything. Any group 1 ion, except for cesium, any group 1 ion is soluble. Sodium something soluble. Same thing as ammonium. Ammonium anything soluble. Same thing as nitrate. Anything nitrate soluble. Okay? So you can just assume most of them are soluble. Now, if something's soluble as an ionic compound, that means that it's a positive and a negative ion, and when you put them in water, they separate from each other. So we say colloquially, like in the common tongue, we say it splits up, right? Have you ever heard somebody say, oh, this thing splits up, right? But it dissociates. They dissociate from each other. So ionic compounds, they will dissociate if they have high solubility. Now, acids, you have to take a look. There's 2 types of acids. What are the 2 types of acids? Strong and weak. Strong acids, do they even exist? In water, no. Any of those top 6 acids, right? When I look at my chart over here, any of these top 6 acids, did we write down on your periodic table that those don't exist? Yes, they're too strong. They immediately turn into what? Hydronium. If you see a strong acid, you need to assume that it is actually hydronium. So a strong acid is actually hydronium and whatever else is present, right? Just whatever else is present, okay? Weak acids. Weak acids will ionize a little bit, but 90% of them, 99% of them won't, okay? So weak acids, you just keep the same as it is, right? Just keep it the same. Bases, there are strong and weak bases. Strong bases, what does a strong base look like? What kind of compounds are strong bases? Jaden? any ionic hydroxide, right? Any ionic hydroxide. So if you see an ionic hydroxide, then dissociate it, right? It's an ionic compound, dissociate it. So we dissociate. By the way, you have this. This is our 0.1 notes. If you were to look at your 0.1 notes, we have this exact table in way more detail than this. But I don't want to bring it up right now. Okay? Weak bases, you just keep the same. What do I mean by weak bases? Like ammonia, NH3 is a weak base. You're not going to split it up or anything like that. And then molecular compounds, you just keep the same. So this is why I tried to do a couple of these. Okay, so I'm going to do one together, and then I'm going to give you the rest of the time to work on these predictions. Then we'll do the lab tomorrow morning. Is that okay? I don't want to stress you out. I don't want to rush this. Sodium hydrogen sulfite is added to a solution of formic acid, and I want you to predict what's happening. Okay. Again, the most important thing for us to do is predict the major entities. Yeah, this is in our 16.2 notes. We've already done this, but I want to go over it again. This whole compound, sodium hydrogen sulfite. If you're ever given a name and asked to get a formula from it, or something like that, this is immediately where your mind has to go. You have to think, okay, what kind of compound is this, right? Sodium hydrogen sulfite. We don't know whether or not to split this up unless we know what kind of compound is it. So what kind of compound is it? Is it ionic, acid, base, or molecular? It's ionic, right? Why? How do you know? How can you spot this from a mile away, Jaden?
Sodium.
Sodium, boom, metal, metal. Anything metal. Metal, ionic. Metal, ionic. Ionic, metal, metal, ionic. Okay? So, metal, ionic. Now, sodium is a group 1 ion. This is going to be able to split up. That's why you see sodium so often. If I ever say sodium something, I'm trying to tell you this is a compound that can dissociate. That's why we use sodium so often. So sodium hydrogen sulfite. That means we're going to have sodium ions present. And then what else? What else are we going to have here?
It's just like
The whole thing together, right? You do not have hydrogen in here. There's no hydrogen. There's hydrogen sulfite. Can you see how these two things are together, right? Ionic compounds are only ever positive ion, negative ion. So if sodium is the positive ion, everything else has to be the negative ion. Everything else in this name is the negative ion. So let's look for hydrogen sulfite. What the hell does hydrogen sulfite look like? Do you have to memorize what hydrogen sulfite looks like? No. It's an ion, right? And it looks like a pretty complicated ion. So go into your table of polyatomic ions and look for hydrogen sulfite. Hydrogen sulfite's in here. It's also in your table of acids, right? But hydrogen sulfite, HSO3 minus. HSO3 minus. So you have HSO3 minus. So we're done with that. It's added to a solution of formic acid. Think I just gave you the name of a chemical. What's the first thought you have to think? What kind of compound is it, right? It's formic acid. This is pretty trivial, right? This should be an obvious answer, but what kind of compound is formic acid? Oh, wow, it's an acid. Yeah, it's an acid, okay? So formic acid looks like HCOOH, aqueous. But let's think. Is it a strong acid?
No.
No, it's a weak acid. So what should we do with it? Yeah, just keep it the same. Don't worry about it. So we've got sodium hydrogen sulfite being mixed with formic acid. And because they're all aqueous, what do we also have? Water. Now that we've done the hard part, now that the hard part is over, can you predict this reaction? Yeah. It's the major entities that kills people. Sorry. And that's the Chem 20, right? And we remember, we reviewed it on the first day of classes this semester. We kind of reviewed it again today. You need to put in the work. Is there going to be one of these questions on the quiz on Wednesday?
Yes.
Yup. Okay, you need to put in the work and you need to figure this out for yourself, because if not, you're going to get hammered on the quiz. And you're going to get hammered on the lab as well. Okay, can sodium be an acid? No. Can sodium be a base? No. Can hydrogen sulfide be an acid? Yes. Can it be a base? Yes. When you look at it, it can be an acid and it can be a base, which immediately should notice that's amphiprotic, right? Right? Could go either way. Okay, HCOOH, formic acid. Can that be an acid? I sure hope so. Can it be a base? When I look at the list, I scan through HCOOH. Nope, doesn't see it. Don't see it there. Water. Can water be an acid? Yes. Can water be a base? Yes. So now that we've labeled all our acids and all our bases, what's the strongest acid? HCOOH is our strongest acid. What's our strongest base? Okay, let's double check, because I'm trusting you on this. I'm totally trusting you on this, and I don't know if I should be trusting you on this. Let's see. When we look at our strongest acid, we see formic acid is our strongest acid. Good, that's fantastic. Okay. When we look at our strongest base, nothing. Oh man, holy book, nothing. HSO3, right? HSO3 minus, that's our strongest base. Okay? I know it's super high on the list, but it is our strongest base. So this thing is our strongest base. So write that the strongest acid transfers a proton to the strongest base. The way I always write this, acid first. You don't have to, doesn't matter. So the acid transfers a proton to the base. So we're going to get H2SO3, not minus. And we're going to be left with HCOO minus, aqueous. What's the very last thing we have to do? Products favored or reactants favored? You tell me. Is this products favored or reactants favored? It's very much reactants favored, right? Yep, reactants favored, okay? Would you agree with me? Would most of us agree that the major entities is really, truly the only difficult part of this whole fiasco, right? Major entities is really the only difficult thing. So that means you got to bone up on your major entities. This lab, these first 6 reactions. The 7th reaction I don't care about because we're going to talk about it, okay? But the first 6 reactions are going to be due by the end of class tomorrow. I am not going to give you time to really, truly work on these reactions in class.